Alright folks, we're going to start at the second part, so it's Measure of Science Part 2. I encourage you to kind of download the notes, follow along as you go, and answer any questions as we start to come to them. So when we start to get into the second part, it deals a lot with taking a look at numbers, seeing which values to keep and which ones to eliminate because of, say, error or rounding error or anything like that. There's many mathematical calculations that are performed when measuring physical properties, and we tend to use the same kind of set of rules across the board, so there's no discrepancy from one place to another, from one scientist to another, from one student to another. Everything is done kind of in a uniform way. So all measurements are subject to different uncertainty based on how we measure them. And I guess to start with, we need to see kind of what that looks like. Precision is the degree of exactness to which a measurement can be reproduced. So if we try to look at the picture and take a look and see kind of your low precision to high precision, you can see that in the first picture, their dots are kind of scattered all over the place, whereas in the picture in the top right corner, it has low accuracy, but its precision is quite high. And that's because accuracy is kind of more of what we think when we start to think of things that are precise. Maybe it's a little bit of a confusion in sets of terms, but describes how well the results agree with an accepted value. And underneath this, I do have a little link that just has an interesting article. It deals with redefining what the weight of a kilogram was. It is pretty interesting. If you have a second, I encourage you to take a look through. So, what are significant figures? The number of digits in a measurement we know for certain, plus one additional digit is considered to be significant figures. So, for example, if you were to look at this pencil, what do you think the measurement of this would be? So it starts off at 0, and it goes over into this 9 point something, right? So we know for sure that we're at 9. And then really what we're trying to figure out is, what is this, right? It's 9 point something. And so if you look at it, you might think, okay, it's 9.1, 2, 3, 4, 5, 6, 7, 9.8, maybe you might say, and then have a quick measurement and move on. But in science, we try to be very exact in what we can be. So that's where we say we know it's all the digits we know for certain, right? We know by looking at this that it looks like it's up to 9.8, but we need one additional uncertain digit to count in, and that's kind of like your guess. Right, we go past whatever the most accurate measurement we can have is. So if we were to zoom in a little bit more, it says, what would you report the length of the object to be if we were to zoom in on it? And so now we can see that if we take a look at it, it's not just up to 9.8, right? This line kind of comes in between here somewhere. So we have to take a guess as to what that uncertain digit might be. So we know for sure, we could say that this is 9.8 centimeters, but really what we need is 9.8 something centimeters. And that something, by looking at that, if I took a guess that that was a 2, that's completely acceptable. You might take a guess that that's a 1 or a 4. Those numbers are completely fine. It's one uncertain digit. Okay. So then there's a little question underneath just for you to think about. What other measuring devices can you think of where significant figures would apply? What about some that won't? So anything that requires measurement by using a ruler, measuring tape, anything where you're taking kind of that measurement where you could have a little bit of rounding in it, would obviously apply to this stuff. And some things that won't, well, if you had something like a stopwatch, for instance, and clicked off your button to measure your time, the number that you get is the exact number that's there. So you'd have no rounding in that case because it's reporting exactly what the number is. Get rid of those. So significant figures have very specific rules in them. And so the 4 bullet points that are here, these are ones that I hope that you can kind of get ingrained in your head, ones that we can follow to just recognize. So they include all non-zero digits. So something like 2.59, for instance, each digit is a non-zero digit. It has 3 significant figures in it. It includes any zeros between two non-zero digits. So we have a 5 and a 7, and there's a 0 tucked in the middle, 507. It also has three significant digits. There's a 0 tucked in between two non-zero digits. So if we were to look at that number, 507 does not really change what that tens place would look like. It includes any zeros to the right of both the decimal point and a non-zero digit. So for example, we've got 4.60. It's after the decimal, and there's a 0 after the 6. So that would have three significant digits in it. As soon as you cross over that decimal point, your zeros are going to count. And so if the second example, if that was just 700 without the 0, so if it was just 700 like that, it would only have one significant digit in it. The zeros after that, they wouldn't count. But as soon as you see the decimal place with any numbers after it, those zeros count, and it becomes four significant digits. They include all digits, so 0 or non-zero, that are used in scientific notation. Digits that are not significant. Any zeros to the right of a decimal point, but preceding a non-zero digit. So in this case, in the first example, you can see that there's no number before the decimal. It's just a 0. It's a very small number. And so we can only start counting when we hit a non-zero digit. So in this case, the first non-zero digit that we see is this 4 that's right here. So in this case, it becomes 0.000045, but the 4 is the first digit that we count. It would have two significant digits in it. Any zeros to the right of a non-zero digit, so 38,000 for instance, there's no decimal that's there. That 38,000 could very well be rounded from something that's 37,995 rounded to the nearest thousands place. So it would only have two significant digits in it. Okay, no decimal, and then if the zeros are after the number, they do not count. So I've got a couple here for you to try. What I'll do is just take a second, go through, make a guess. If you have the notes in front of you, write it right on there. You can write it on a piece of paper and just make a guess. And then when you're ready, just kind of resume the video. Alright, so I'm going to click through each one and just kind of run through the answers for them. And you can kind of take a look and see how you made out with each one that's here. And if there are any that maybe, might have confused a little bit. So the 425.6, it would have your 4, 1.05 has 3, the zeros in the middle, 9.6093, 5, and then you can start to kind of follow through the list that's here. The only one that's really different than what we talked about, it wasn't just in that last slide talked about scientific notation, that's this 173.2 times 10 to the negative 3. So all the digits, not the times 10 to the negative 3 part, that just tells you where to move the decimal, but all of the digits that are in the actual value itself, they count for significant digits. So that's why there's 4, because there's 4 digits right there. And if this is something that you need a little bit of extra practice with, I encourage you to try these out. And then I also have a little link that I made on the bottom that has it's called Quizlet. It just has a little thing where you can kind of test your speed with different significant digits to go through and just see how you make out. So if you'd like, take a second with these, pause it, try them out. I'll write out the answers here in a second. Alright, so for the first one, 3.0 times 10 to the 8, remember the 3 and the 0 are the only ones that count, so this one would have 2. The 0.7, it starts off, the 0 is leading, so it doesn't count, which means it's just the 7, it has 1. 9.7, both digits are non-zero, it has 2. 15 million, all these zeros afterward, there's no decimal there, so that's likely a rounded value, it just has 2. 6.7523 would have 5. 3.45 would have 3. All of them are non-zero digits. Here we've got a leading 0, but it's after the decimal. So as soon as you see a non-zero digit, all the numbers after that will count because it's after a decimal. So it starts at that 4, which means the 4, the 1, and then that last 0 are going to count. So this one has 3. 9.109 times 10 to the negative 31, that's scientific notation. So remember, all of the values in scientific notation count, which means this one has 4. 0.08905, that one has 4. First number after the decimal, and then on from there count. 4.501, it would have 4 in it as well, as soon as you start with a non-zero digit, and then after the decimal, the rest of them will count. 440 micrometers, so it has no decimal after it, which means that last zero does not count. It only has 2. 4.0, there's a decimal, the 0 is going to count in that case. 6.02 scientific notation, it's the same thing as this one, so it has 3 in it. 0.00465 starts at the 4, so it would have 3, and then the last one would also have 3. So again, if you want some extra practice, I encourage you to try the little Quizlet, just to make sure that you have kind of an understanding of how to do it. Some quick housekeeping items, rounding. So if the number after the digit to be kept is significant as a 5 or greater, you round up, and then if the number is 4 or less, you round down. So basically, if you're rounding a value, you always look at the digit after to be rounded, and then you take a look and see, okay, is it a 5, 6, 7, 8, or 9? If it is, you round up. 0, 1, 2, 3, or 4, you round down, or keep it the same, I should say. So important, never round a value too early if there's multi-step calculations, because if there is, it will throw off your answer. Always work out your numbers with all of your digits, and then just go back through and start to figure out where your significant digits are coming from. Alright, so a couple other little rules now. We're going to start to get into adding and subtracting. So you can see for the first one, and then later we'll go into multiplication and division, but they do have slightly different rules. So when adding and subtracting significant figures, the answer, the sum or the difference, so the addition or the subtraction problem, has the same number of place values as the measured value with the fewest place values. That sounds really confusing. Basically what it's looking for when you add or subtract is you're looking for your least accurate number. So a number that has more decimal places in it is far more accurate than a number that is a whole number. So if we take a look at our first one, and I have 12.45 and 4.2, when I add those together I get 16.65. But if we take a look and see which number is the most accurate here, well, the 12.45 is more accurate than the 4.2. It goes to an extra digit. So I can only round my answer to the value that has the least accurate measurement, and in this case it's the 10th place. So that means I have to round my number to the 10th place. So that 5 at the end is going to determine if that stays as a 6 or goes up to a 7. So if it's 16.6 or 16.7, and when we report our answer, 16.7 from the rounded value. And then the same thing for the next two. The 3.26, right, goes 2 digits past the decimal. 5.4698, 4 digits past the decimal. Add them up, don't round anything early or anything like that. 8.7298. And then when I take a look, the 3.26 is far less accurate, which means that I can only go 2 digits past the decimal. So I'm looking at this 2, and I'm trying to figure out, is that going to stay as a 2 or go to a 3? I look at the digit after it, it's a 9, so 8.73 kilometers as my value. The very last one, same thing, 7.8521, 0.032. If I take a look, I've got 4 digits past the decimal, and in the other one, I have 3 digits past the decimal. So if I go 3 digits past the decimal in my answer, that 4 is going to stay as a 4 because that 1 is low. So keep going on with the next part. Addition and subtraction is just going by place value. If I take a look at multiplication and division, when multiplying and or dividing significant figures, the answer has the same number of significant figures with the measurement with the fewest number that's there. So 6.71 times 7.850. In the last one, with the addition and subtraction, you're looking at place value. When you start to look at multiplying and dividing, it's all based on significant figures. So if we count significant figures out, 6.71 has 3, 7.850 has 4. That means that my answer, regardless of how long it is, can only have the value with the least. So this one has to have 3 significant figures, which means it's going to go 5, 2, and then 6. and then we need to figure out if that stays as a 6 or if it goes up to a 7. And because of rounding, we can see that it's 52.7. Similar with the next couple of them. The next one would go through 2.4. It would have 2. 0.08 only has 1, and so I have to round it to 1 significant digit because that's my fewest significant digits in my question. So I'd actually have to report that answer as 0.2. And then just kind of continuing on, the next one has 4 for the smallest value because the 39.7525 would have 6. And so if I have 4 here and 6 here, I'm going to need 4 in my answer. Now, this one ends in a 9, which means that if I were to round that up, that would actually carry a 10, which would change the 8 in the 10th place, or sorry, in the 10th place over to a 9. So I'd have 16.90. Division, same steps. 44.794 divided by 19.13. I get 2.34 and a whole bunch of stuff. We have 5 significant digits in the first one, 4 in the second one, so I'm going to have 4 in my answer, 2.342. Okay, notice that for all of them, the units are at the end. Units are very, very important. Please, 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 please include your units. So I mentioned these double step problems from before. So if we have a multi-step problem, you treat it the same way, use your order of operations, keep track of significant figures throughout the problem. So we're going to subtract first, following order of operations, and then we're going to divide. I need to take care of essentially brackets, right? So really, we treat this problem like there were brackets around the top part. We need to figure out and simplify that top part before we can do any division. So if I do 1.07, and I'm just going to make this just a little bit bigger. I can write on here. So if I subtract to start off with 1.07 and 0.8826, we get 0.1874. So 0.1874. I'm going to divide that value by 0.762, and then in my next step we'll actually do the division. So first step is just the subtraction, next step is do the division. 0.24593, 0.24593, and that gives me an answer of 0.25 altogether. Now, how did I get to that 0.25? How did I know it was 2 digits? Well, go back through your answer. The first one is a subtraction, so we need to go by place value. This one goes 2 places past the decimal. This one goes 4. That means when I subtract, I can only go 2 digits past the decimal. If I go 2 digits past the decimal, then I have 2 significant figures when I divide. This one has 3 significant figures when we divide, which means that I have to use the value that only has 2 significant digits as my answer. Because the 5 is after the 4, that's going to round up that 4 and make it 0.25 as a final answer. The next one, 82.7 and 0.18. So do the division step first. 82.7 divided by 0.18. I'm going to get 459.4 repeating. And then we're going to add that to what we originally had, 114.25. Now, if I do the division step here, I can see that I've got 2 significant digits because 82.7 has 3, 0.18 only has 2. So if I have 2 significant digits here moving forward, that actually becomes my place value in my next step when I'm adding these together. So add them like normal. You're going to get 573.694 repeating. Now, when I add them together, notice how this one only goes to the tens place, and this one goes all the way into the hundredths place. So when I add these together, I need to go to my least significant place value. That's the tens place. So in this case, this value is going to go to 570 as a final answer. So I hope that gives you a little bit of an indication on how to do these questions. The next step, the last part of our Intro to Measurement unit, is on rearranging formulas.